Very good. So let us then start. So we are happy to welcome Professor Qian as our speaker today. So I will provide some short information about him, and then his website is very well structured. So for more information, you can look it up there. So Professor Qian did his bachelor studies in Beijing, China. And in those days, he was studying astrophysics. Then he moved to US, and for the rest of his career, he is doing statistical physics, biophysics, biochemistry, and chemistry. And so all these directions are somehow mixed in his activities. So he did 2 postdocs, one with Hopfield, and then moved on with applied mathematics and statistical physics and subjects I mentioned. So one of his distinguished points is that he is versed both in physics and chemistry, and in particular in biochemistry. So to my understanding, it's very rare that somebody is really doing well in both these subjects, because they are quite complementary to my understanding. So Professor Qian is very productive. He did more than 200 papers in various leading journals. And he developed, he was one of pioneers of stochastic thermodynamics, by the way. This is a subject of statistical physics, which is focusing on thermodynamic relations for small systems, systems which fluctuate, systems which are out of equilibrium. And naturally, those systems are very important for biology. Now, for today, Professor Qian will tell us about more statistical physics-based work. As far as I see, there will not be much biology here. So please, Professor Qian, please start.
Thank you. Thank you so much. And really, I want to thank David and Armand. I have never met, to invite me to give a presentation of our recent work. So this is a work mainly was my focus for the last 2 years. And as I introduced, I had a more practical, real, even experimental experience working with statistical thermodynamics on biologically related systems. But in last several years, we start to see a very interesting different direction. That is, I believe the current textbook teaching of Gibbs statistical thermodynamics needs to be revolutionized, because there's really much more fundamental underlying mathematical foundation in the Gibbs theory. And the current teaching, which has already been 100 years old, more or less, ever since Gibbs published his book, can have a much more exciting foundation, very much like quantum physics, which we all know need a certain very clearly defined mathematics. So this is my goal. And one thing I just wanted to catch your attention is, in this talk, I mainly talk about Gibbs theory and statistical physics, but you can actually start to see a possibility to understand the Newtonian mechanics and maybe even quantum mechanics through a very different lens. I just would shout out the controversial or the provocative statement. Maybe there's an entropic basis for all these other physics theories. Okay, let me start. So the first thing I want is trying to catch a few more mathematically minded audience. So Giancarlo Rota, who is one of the leading 20th century applied mathematicians, who in this very interesting book said this statement I always treasured, because this statement seems to put what I'm doing in the right place, which says it is a standing between physicists and the mathematicians that thermodynamics cannot be axiomatized. As you all know, Hilbert's sixth problem tried to axiomize all the physics and the geometry and quantum mechanics and classical mechanics and electromagnetism. All those theory has very well-defined mathematical foundation. But the statistical physics and more importantly, thermodynamics was never clear what is the mathematical foundation. We use math, but it's very elementary mathematics. Now, since I'm talking about statistical physics, we cannot escape starting with statistical mechanics. I want to emphasize mechanics is the starting point for these two giants. One is the Boltzmann, one is Gibbs. But I like to now already immediately to draw attention. Most textbook tells you these two giants worked on the same theory with the same scope, which I believe is not the right thing to characterize them. In fact, I would like to say the tenets of the two theories developed by the two are different. For Boltzmann, he really just wants to provide thermodynamics a classical mechanical foundation. Since classical mechanical foundation is well laid out in mathematics, therefore Gibbs program literally is applied mathematics, and it's very hard, difficult. So that's why even today it's considered have a challenging problem. In fact, one of the field medals given by Cedric Villani a few years ago was exactly along that line. It's a very, very mathematical, if you want to be rigorous. However, but what he did, in order to carry out his theory, of course, the very first thing is introducing the concept of the entropy into classical mechanics, which doesn't exist in the traditional Newtonian mechanics. Is his famous formula, entropy related to the probability. Gibbs, on the other hand, I would like to argue, really has a very different tenet. For one thing is, Gibbs theory showed you there is a whole set of mathematical tools, starting with partition function. You can derive in the limit of infinite large system all the results and the relation and the concept in classical thermodynamics. But more importantly is, then you can apply the same system of partition function and computation to do system with the fluctuation smaller and smaller. There's no other justification except the Gibbs theory give you prediction. You can compare with experiment. If it works, you can keep doing until one day we find it doesn't. This is the fundamental nature of any physical theory, right? And as far as I know, in the last 20, 30 years, the most exciting place of applied Gibbs theory actually is in biology, outside quantum mechanics. In classical mechanical region is in biology because single molecules, these things is very small, but the Gibbs theory so far still working very well. Nobody reported anything significantly violated Gibbs theory. So therefore, I would argue they're different. Now, I also like to draw another very interesting historical, now I consider very important. You can tell me whether you agree with me. On the left is the famous book Gibbs published. In 1925, Szilard published his PhD thesis. So this is one of Seilard's paper, much less known. He has a much famous paper on Max Demon, had thousands of citations. This one only have like less than 100. In this paper, however, Szilard laid out a theory which he called phenomenological thermodynamics with fluctuation. In other words, this theory has no atomic picture. Neither he even require atomic picture of matter. He really just go after the thermodynamical formalism and using the now we know very clearly, as I will show you, a statistical argument and included the fluctuation. And this was very difficult for most people. Even until 1960, Mandelbrot was the first person clearly identified the mathematical underlying in Szilard theory. So Mandelbrot wrote quite a few papers, which is the one starting on the left, right, to point out the whole foundation of Szilard theory is actually what is called the Fisher-Neyman theorem in statistics, pure statistics. So one of the unique consequence of Szilard theory actually is the concept of temperature fluctuation. That, of course, many of you may be more interested than anybody else is because Landau, as a physicist, was the first one start talking about temperature fluctuation. But in the West, this is always considered to be non-orthodox, in fact, to be wrong. So that's why there's a debate between the famous physicist Charles Kittle and Mandelbrot in Physics Today, 1989, try to argue whether the concept of temperature fluctuation is even valid concept or it's the wrong thing to do. Nevertheless, this just shows there's another statistical thermodynamics without the atoms and the molecules and the picture of Boltzmann and Gibbs. In fact, without mechanics, you could say. Now, I like to present a few simple but clear mathematical results I need in order to build my understanding of Gibbs theory. And that is basically a asymptotic result beyond the law of large number. And it is under the name called the Sanoff theorem and Cramer theorem, which I will introduce very quickly. Here, this is something everybody knows here. That is, if I have a sequence of identical independent random variable, x1, x2, all the way to xn, and if I compute their arithmetic mean value, it has a very well-defined limit, which converges to the expected value of the random variable. This is called the law of large number. There is a similar, different theorem, if you want to emphasize the nature, is you don't actually measure the value. Let's assume, just for simple physics argument, it's a discrete state system. Then you just count the number of times a particular system in particular state. There's no number to measure, they're just counting the time. And the fraction of the time the system stays in state I will eventually in the infinite sample converge to the probability of that state. That's another version of a law of large number. Now, what I'm going to use again, in fact, this is the foundation, I believe, not only behind the Gibbs theory, fundamentally it's behind the thermodynamics itself I want to emphasize. Where does thermodynamics come from? We've always been told because energy conservation. I try to argue, no, there's a fundamentally different reason, at least possibly, without mechanics. So here's the idea. The previous slide showed you when n increase, eventually the probability distribution for the mean value converges to a single value, which uses a physics language as direct dirt function in the red here. But the process of convergence, mathematicians showed, can be always expressed in terms of asymptotic rate on the exponent, with this n going to infinity. Of course, for every x except the peak value, this whole thing has to be 0. So this phi must be positive everywhere else except the single point, which is global minimum, which is 0. The existence of this phi function is the mathematician's interest. Compute its form. If you can, then do it. If you cannot, mathematician doesn't care, but we are the physicists, right? So we are interested in how to compute it. So from now on, I mainly just talk about the form of this function. But why this function interesting is, in fact, these two lines of mathematics here. That is, you see, if I have a region in the X space, I'm interested in its converging to 0, right? Outside this point, every set is the probability eventually goes to 0. But if every set the probability goes to 0, there is a rate to go to 0. But we all learned in college, in calculus, if you have many terms add together go to 0, it's always determined by the slowest rate going to 0 asymptotically. So therefore, ultimately, the rate of this set going to 0 really determined by the global, by the minimum on that set of this function. And this is the importance of this function. But it's also the beginning of optimization, minimize free energy, maximize entropy, and all those other things we talked about in thermodynamics. And I will come back to this. So fundamentally, mathematicians prove the existence of this function with certain mathematical property. We can compute it, but the importance of this function is it can be used to get other things through optimization and maximization or minimization, depends on the sign. And I will give you one example very soon. I jump through this one. Okay, so now let's introduce the Sanoff theorem. Sanoff theorem says the following. Sanoff says, let's just do a simple one. Assume I have a discrete finite state system. And of course, if I have such a system and I do repeated the measurement capital N times, and I just count how many times is in state I, and divided by total N, this becomes a frequency, relative frequency. Then this relative frequency converts to probability when N goes to infinity, as I mentioned to you earlier. Then the Sanoff theorem says you can compute the log of the probability divided by N minus sign. This gives you exactly the phi function I showed you earlier, and has this very explicit beautiful form, which is widely known in many different areas. Some area called relative entropy, sometimes called KL divergence. Shannon used it by assuming the PK is uniform. It shows up everywhere, and it's being even considered as the fundamental starting point. I just tell you, no, that's not a fundamental starting point. That is only when you're dealing with identical independent sample, this becomes a fundamental. But when you're dealing with the other system, it will not, as I showed you. Nevertheless, this is a very important function. And this function gives you the phi function I mentioned earlier. Now, with that function in hand, let's show how this can be used very usefully. Let me try to use that function to derive a theorem which came out actually earlier than Shannon. It's called a Cramer theorem. It says the same system, instead of measuring the frequency, let's assume I have a random variable called y on the system. And then you just do repeated measurement of a single this random variable and construct the empirical mean value. And of course, large deviation, large number says it's going to this expected value. Then the mathematician, the Cramer theorem, said there is a function. In fact, it's convex and continuous if the original distribution is nice enough. Now, I'm interested to compute this I instead of prove the existence. What is I? The I is very simple. I is the constrained optimization of the original Shannon function, conditional on, because when you have a frequency given in F, then the corresponding arithmetic mean value for y is just this sum, right? It's just different to count. You can count the mean, you can count how many times each happening and multiply. So constrained on this equal y and find the particular set of F, right? This is the idea. Every F is even less likely. This is the only one relevant. We'll give you the new function I. If you go through the drill, this is the result. The result says, this is the procedure, mathematical procedure. You suppose construct something called a cumulative generating function, which involve a new parameter called beta. And here's the random variable y. After you get this function of beta, you do the Rand-Fenchel transform through this soup. When you do that, in fact, the I and the lambda has a dual relationship. So this is the Cramer theorem, including how to compute the I through the cumulative generating function and the Laurent transform. Okay, it's pure mathematics. It's very clear. Now, let me do one thing, which a mathematician never do, because this looks less beautiful. But to you guys, probably you will realize this is much more interesting. The soup maximization of this quantity, of course, I can use calculus. Now, if I use the calculus, means I do derivative respect to beta, immediately give me y equal the derivative of lambda. And I plug in this thing into the equation and rearrange the whole thing. I get a new result in terms of derivative. Okay, just notice it's a little strange. I use the cumulative generating divided by beta and then do a derivative respect to 1 over beta and then with a minus sign. This is just a formula. This is exactly using calculus to accomplish this minimization or maximization, sorry. Now, let's switch to Gibbs equilibrium statistical physics, the thing we learned procedure-wise usually. We start with, again, do the simple thing, assume discrete states with mechanical energy E and degeneracy P, we calculate partitioning function. And after partitioning function, we multiply KT, change sign. This, the only thing we are interested in is quantity because thermodynamics tells us this is Helmholtz free energy. And Gibbs showed it in the limit. And then entropy relate to Helmholtz free energy through famous thermodynamic relation with temperature is basically this formula. You know what? If I identify temperature with -1 over beta, the Helmholtz free energy with a unit of Boltzmann's constant and divided by beta, and S, the entropy, Gibbs entropy as K times my I function with a minus sign, this red box is exactly this result. In other words, off by a minus sign, from now on, entropy can be maximized and minimized. I'm not going to strictly use this language. Plus a unit called KB. This is Cramer theorem with given large deviation rate function for random variable. Now, don't forget, I also showed you the Shannon's entropy is actually the large deviation rate function. That phi function is called the large deviation rate function for frequency. So you suddenly realize these two famous entropy are really exactly the same thing. But it's interesting, even today, you can argue to people ranging from, oh, they're completely identical, same thing, to people completely different thing, you shouldn't mix them. The opinion is widely varied, and there's no consensus. I would like to suggest they are fundamentally exactly the same thing due to these two different forms of law of large number. So using a language, Shannon's information entropy, note two things very important. The first thing is, in this theory I'm presented, a thermodynamic quantity is very important as a function of which independent variable. This is never emphasized in statistical physics. It is quite emphasized in thermodynamics. We know there's a set of controlled variable, a particular ensemble, then they have a corresponding thermodynamic potential. But then we start talking about any other quantity as a physical quantity without a reference to what is the independent variable. The mathematics is much more careful. You have to talk about function of whose variable because they will be different, right, when you do Lagrange transform. So Shannon's information entropy as a function of empirical frequency, the whole function of empirical frequency is to a Gibbs thermodynamics entropy as a function of internal energy. So therefore, Shannon's entropy actually has a role in statistical physics. It's just not clear, as I'll show you. And it is this relationship is the same thing as the law of large number for empirical frequency or for empirical mean value. That's why you have two law of large number, you have two entropy functions. Now, let's do one more mathematical exercise, since we already start to have more mathematical tools to play with. So here is, again, Shannon entropy in the more general form, relative Shannon entropy. If I want to calculate the Lagrange transform, right? Because Lagrange transform we discussed is important in Cramer's theorem. But don't forget, there's a constraint on F. Under this constraint, work out the mathematics, we got this result. So you see, we are getting back almost look like a log partition function again, except this time, the new set of parameter is this thing on the exponent, very much like a minus mechanical energy, use KT as a unit. And then, of course, having this property, you can calculate the frequency and the conjugate variables through derivative. Therefore, now here's the more interesting. Shannon's information entropy has two rows now. Has one row. As a function of the empirical frequency, it actually gives the thermodynamic entropy as a function of internal energy, right? They are different functions. They have different names, but more importantly, they have different independent variables. And that is parallel to the same Helmholtz free energy, either as a function of the state of all the mechanical energy. This result as a function of U. We never think this way. Or say same Helmholtz free energy as a function of inverse temperature. So that is why Helmholtz free energy is so important in statistical thermodynamics. It has two roles to play, either the function of beta, which is way familiar, but also the function of all the energy of mechanical energy, which we never think that way because we believe we already know what mechanical energy is. Therefore, Shannon's entropy really should be part of Gibbs theory. Any statistical thermodynamics book should talk about Shannon's entropy, derive its formula, relation to Helmholtz free energy. It's just part of the story. Now, let's connect this to more authentically the statistical thermodynamics. The most important difference, in addition to the minus sign, is actually the entropy in thermodynamics and statistical physics is extensive quantity. Therefore, in fact, it is related to my phi function through this relation. Everything here is extensive, i.e. I don't normalize by the V. I use the sum. But large division rate function is a function of intensive quantity because they are in the limit. So therefore, you have this whole entropy expressed in phi function, and it's immediately obvious. This is a homogeneous order one function of V, E, and N. Euler's homogeneous order 1 function. Such a function always has the important property which gives rise to these new quantity called conjugate variable, but in physics has their own name. And more importantly, the total derivative. But we notice this is basically fundamental equation, Gibbs equation, fundamental thermodynamic relation. Now, something more interesting is going to happen. If that is true, then the Lagrange transform of a homogeneous function is 0, right? Because this is the conjugate variable times the variable itself. Lagrange transform is supposed to be used S, subtract this term. So you end with the Lagrange transform is singular. It's almost 0. With that, you immediately get a new result. And if you rework out this result, you realize this is famously called the Gibbs-Qian equation in statistical physics. And interestingly, this equation, if you ask a physics professor, this doesn't seem to even pay attention to. They said this is chemical engineering. But in my theory, this is fundamentally important because this is due to the fundamental theorem in a very subtle way, as I will show you. So Gibbs-Qian equation is just a flip all the term, but it equals 0 instead of equal something else. So there's a duality relationship between a rate function and its due. And if this rate entropy function is homogeneous, then you always have a Gibbs-Qian equation. Gibbs-Qian equation really is saying the following thing, saying these 3 parameters, T, P, and U, these are 3 conjugate variables. They satisfy a mathematical equation. But the form of the equation depends on a particular system, particular material. You have to work out and find out as an engineer. The thermodynamic theory only claims there is such a relation, which is called equation of state. So you see, this is the fundamental importance of a physics theory. They basically suggest that there is such a relation, but the detail of the relation always left for the engineer to figure it out. So Gibbs-Qian equation is just the differential form of the existence of such a mathematical relation between these quantities called equation of state. But don't forget, all the conjugate variable is just a partial derivative of entropy respect to these extensive quantity. Therefore, any equation of state actually is also a differential equation, if you are willing to write them as a differential equation for the entropy. And these differential equations are first order in mathematics and applied mathematics is called Harmonic-Jacobi equation. So now here comes the second insight. The thermodynamic equation of state actually is the Harmonic-Jacobi equation for entropy. It's the same equation, it's just different way to write it. We use conjugate variable or we use a differential. Now, this is in the limit of n go to infinity. What happens if I have a system have large number but not infinite? A good physicist always applies that kind of theory for the infinity back into finite system. And let's see what we can learn there. Here, I need to go ask a more fundamental question of what is probability? How do we use probability to do science? Let me just work out one simple example. Here, I have a Bernoulli random variable called x, i.e. they take only 2 values, 0 or 1, with certain probability being 1 called p, and the remaining probability 1 minus p equals 0. Let's say I have identical independent capital N measurement of the same quantity again, and the sum give me k. But I'm going to condition on having this equal k and ask again what's the probability posterior of x1. Now, by symmetry, we know this will be the same distribution for x2, x3, or the x after the constraint, because the constraint has it's completely symmetrical with respect to all the x, which started with identical. Now, some simple calculation showed you immediately get k divided by n. Honestly, when I see this real, I was surprised. I don't know about you. Some of you probably surprised. Some you probably said that's obvious. Let's argue this is profound. For one thing, you realize the probability of the Bernoulli random variable completely independent of the P anymore. It doesn't matter what the original P is. It's simply just equal what you observe. There's no relevance of the original P you assume. Of course, it's very important. In this case, if you ask the joint probability, you realize they are not independent. This thing is not K divided by N squared. So therefore, after constraint, these X1 to Xn are not independent. They are very different kind of object. But nevertheless, their posterior distribution for a single element completely determined by the measurement. In other words, you can assume any probability that you want. When you have the real data, the assumption just gone. You can basically replace the assumption by a more reasonable experimental fact. But they deserve a lot of discussion, because here we start to touch on what is really probability, what is conditional probability, whether probability should be interpreted as a frequency or as a Bayesian. And I like to argue a third way, which is what we call statistical physics way. Now, let's go back to even more fundamental Kolmogorov's theory of what is probability. He says, in this particular problem, each random variable has X, 0 and 1. But let's do this simple example, capital N is equal to 10. In this case, Kolmogorov told us we need to have a probability space based on the state space. The state space is this thing. It's all the possible sequence of 0, 1 with 10 elements. This is the complete probability space. And then what I showed you equal K is just one particular situation in this one. Let's discuss this situation. So here's several scenarios in a very elementary probability. Started with the one. John basically has such a coin. He tossed it 10 times and observed the 1 head and the 9 tails. Now, let's think about it from a probability theory. What he should do? Should he conclude that the coin is very badly made? Or he should conclude he just had a very unlucky throw? The truth is nobody knows, right? If you don't have any prior information, nobody knows. Both cases are good. Okay. Now, Jane, on the other hand, did something a little bit different. She tossed the 10 identically statistically made coins, and they are all landed on the table, with one is up, but it's the 5th one, and everything else is down. Note, according to Kolmogorov's theory, any one experiment completely fixes the one element in this thing. This is the fundamental Kolmogorov theory, is one experiment completely fixes this thing. So therefore, according to Kolmogorov, any experiment completely fixes all the possible things, including the 5th one is up, everyone's down. But by then, there's no probability, there's no relevance of anything. This is a reality, 1 up, 9 down on the table. Probability is gone. The experiment is over. However, now what happens if Jesse is being told by Jane, but she didn't tell him all the story. She just said there's 1 up and 9 down. So therefore, Jesse only have a partial information out of that one experiment. And in this case, Jesse has to do another statistical model. But think about it, this statistical model has nothing to do with the original P anymore. This statistical model has everything to do with the odds of 9 to 1 of these coins. Of course, ultimately, you could do this 10 again, build a frequency interpretation, but that's not what I needed. I'm claiming Jesse is the statistical physicist. He does not really need the original P for the Bernoulli random variable. What he needs is the 1 to 9 odds observed on the table. There is a second model after Kolmogorov, conditional on the observation. And in fact, what he gets is supposed to be a maximum entropy principle with symmetry. Remember, I argued the symmetry, and I will show you a little bit more of that. So there's a symmetry behind the thing, and the symmetry dictates certain new probability, which has nothing to do with the original Bernoulli random variable. It has everything to do with the particular result of 1 up and 9 down. And this idea, conditional on seeing a value in the large deviation theory, in the theory is called Gibbs conditioning. It is a combination of limit theorem, frequency interpretation, and a posterior Bayesian argument. So it's really a more sophisticated than these arguments in statistics right now. And more importantly, there is a shift of emphasis. We don't really care about the original chromograph measure. We are much more interested in what kind of observable and observation will lead to certain symmetry breaking. What is statistical physics really is, I try to argue, is giving a parametric family of distribution conditional on observing a quantity. So basically, statistical physics is give you a model, already know what kind of a measurement you're going to do. And when the measurement comes, it will give you a distribution. But the measurement comes into the model as a parameter. So therefore, it's always a parametric family of models instead of just a model. It's a family of models with something to be determined. And in the case of this x1 ballooning random variable, I can generalize to anything in general as a discrete state. Conditional on having this limit is equal G bar. You can mathematically show this is going to be your canonical partition function. And the canonical partition function, the canonical distribution is the posterior distribution conditional on having the G beta. But the G beta come in through a relationship with its conjugate variable. That's the important thing. Is the model itself has a conjugate variable, but it is just a parameter to be determined by the G bar. The relation are given here. Now, what's the significance of this thing? This turns out to be exactly Seilert's idea. In fact, in the statistics, there's a theory called the Pitman-Koopman-Darmois, which defines a concept called a sufficient statistic, which originally came from Fisher and Neyman. These quantity G are the sufficient statistic of these beta parameters. And for such a system, they always have an exponential family of models. And this is where Mandelbrot realized Seilert theory and thermodynamics can be understood just as a parametric family of models. But I basically showed you this is also a consequence of large deviation theory. So therefore, Gibbs theory and Seilert theory is unified in this mathematical framework. Now, if you have a set of measurement on the frequency, not just a single random variable, you can do the exactly same thing, and you realize something even more interesting. You realize the original probability pi now is multiplied by this factor e to u. And the u is the conjugate variable. So you look at this formula, you realize the original assumption of the p is no longer relevant because any assumption of p, you just have the corresponding u. So therefore, after measurement, the relevance of the p is gone. You can assume p is uniform or anything, and then use the measurement to determine the u. Here comes a new idea. Maybe after all, the concept of energy, even mechanical energy, really is just this quantity to tell us the measurements have this frequency. In other words, energy maybe is a consequence of doing sample with frequency. So if we idealize large data, then what I showed you is we changed the emphasis from originally probability theory emphasize a probability distribution in chromograph theory, now ended with much more interested in this u parameter. The p become almost irrelevant. But this u parameter is nothing but the mechanical is the energy in physics, right? So we are changing from interested in probability to change interested in a set of energy parameter u. That's why it looks like it's a transition from just doing statistics and inference to become doing statistical and physics. So it's now very clear we can start to argue statistical physics does not really, can at least build up without mechanics. Instead, start with entropy. Now, here are 3 theorems. Very quickly, try to show some very important and philosophically surprising consequence. So here's one simple theorem. Let's just go through it. Let's say I have many pair of xi, y, x1, x2. They are a pair of random variables. I do them many times, n equal 1 to 3. And then, of course, according to the theorem I showed you, there should be a large deviation rate function for their mean value x1, x2. More importantly, there's a Lagrange transform as a function of beta 1 and beta 2. Now, what happens now if instead I decide to do just x1 plus x2 and only observe their sum? In this case, if you go through the mathematics, you'll realize the new random variable, the new Lagrange transform will have these two x1 and x2 with the same beta. You see, the conjugated variable being equal, which actually comes from we made addition of x1 plus x2. Anytime when we add x1 plus x2, that means we believe they're, in some sense, they are the similar same thing, right? We didn't add ax1 plus bx2 means they are roughly in the equal weight, and they can be added means they're same kind of quantity. So therefore, the very nature of have same beta actually already in our assumption about the x1 to x2 can be added together. So I'm trying to say the notion of thermodynamic equilibrium is already in the assumption we can actually treat the two random variables as the same, statistically identical in some sense. Otherwise, you shouldn't add them, right? So no wonder if you treat them same, they will come up with the same beta. You can also ask the next question. So yeah, this is basically saying the very act of summing the two random variables together statistically makes them equivalent. I jumped through these two theorems. So therefore, what I showed you here is we can build the whole statistical thermodynamics without mechanics to understand how these thermodynamic behavior. And these are fundamentally based on two things. One is called the contraction principle, which is how you can describe the system through frequency and then understand all the things about random variable. And this Gibbs conditioning, which gives you a posterior distribution. Now, so far, I always talk about identical independence. And we always use Shannon's entropy as the Sanoff entropy as the most important one. But now, Sanoff entropy is not the only thing. If we're interested in Markov chain, the result changes. Some more surprising results come. What happens now if we're interested in a sequence of X? They are not independent, they are Markovian. And in that case, we're supposed to use the transition probability Pij to describe their statistic. And of course, coming with the Pij, there is a stationary probability associated with, let's call it a pi. But if I'm start to measuring in a long sequence, all the pair distribution with I followed, the J followed the I, then there is a large deviation rate function, also we can call entropy function, has this form. They look similar, but no longer the same as the Sanoff relative entropy. More importantly, for these new, there is something called shift invariance. The shift invariance really is saying in the infinite long sequence, the first index, the frequency should be exactly the same second, right? Because they're really just shifted by one in finite length. So therefore, infinite sequence, they're exactly the same. So this is a constraint always there for this function. For any pair sequence not satisfied by this, the large deviation rate function is infinity. Now, using this theorem, we can ask what is the conditional probability conditional on observed a set of new that will give by this matrix Pij times EUij, you realize the original Pij is almost doesn't matter anymore, except for anything equals 0, it's no longer relevant. But for anything non-zero, it doesn't matter. You can make them into 1. The more important thing is this Uij. And what do? We take this matrix, we find its largest eigenvector lambda and the corresponding large eigenvalue lambda, and then the corresponding eigenvector, and construct this property. And then you can easily show the new invariant probability is Vi times Wi. You see something interesting? The stationary probability is no longer just the right eigenvector. It's actually the product of left eigenvector and the right eigenvector term by term. This thing never shows up in the probability theory traditionally, but we see this all the time in quantum mechanics, right? This is the probability of state I using left and the right eigenvector. Now, if instead of observe a pair frequency, I can observe a singleton frequency. If I observe singleton frequency, I can do contraction principle. You can work out the mathematics. Eventually, you realize I have another new matrix B. And the difference from matrix A is all the coefficient, all the exponent, the new Ij is equal to eta I. So all the different J has the same conjugate variable. This is exactly the result of equalized. When you add them, literally they become equalized. Now, the next part is my thinking beyond statistical physics. And I'm not trained as a physicist, so I really don't know anything about a modern, fancier physics. But seems to me, we can start to think about classical mechanics in terms of this theory. Now, here is the simple understanding. Classical mechanics is about a velocity and the motion and the movement. Traditionally, we're always being told that velocity is defined as the delta x divided by delta t when delta x delta t equals to 0, as Newton's calculus. But if we believe any physical measurement of velocity ultimately involve a much smaller world in which everything is stochastic and random, then the same velocity can be understood as a large x and a large t and their ratio. Therefore, in other words, a velocity in the physics could be understood as a very, very long measurement and average over the distance in a much smaller world with stochastic randomness. Then the existence of velocity is no longer the limit of this thing, but actually is a law of large number. And in fact, it's a ratio of two extensive quantity. Extensive means increase with t. As long as I have this idea, then you can build a entropy function. You will obtain a Harmonic-Jacobi equation, as I showed you already. And we all know Harmonic-Jacobi equation and the Lagrangian principle are the basis for Newtonian mechanics. But nobody actually knows why, right? So here we clearly show you can build classical mechanics by identify Hamiltonian as the conjugate variable to time. Then partial entropy, partial time will give you Hamiltonian. So this is my suggestion. And here is a paper we posted recently on following along this line of argument. Try to argue maybe there is a different way to understand classical mechanics, not through this deterministic differential equation, but as an emerging phenomenon through an entropy theory. Assume there's a microscopic world. I want to thank my collaborators and colleagues and the graduate students. Thank you very much.
Thank you very much, Professor Qian.
Thank you.
Shall we move to questions? You can just unmute yourself and ask your question.
May I start?
Yes, please.
Sure.
Well, first of all, thanks for the interesting talk. So my question is that it's less of a question, more of an expression of not understanding. I mean, the thing is that I don't see how you took into account the fact, and I don't know whether it is a fact or not, that we are talking about equilibrium statistical mechanics. So what prevents me to do all these reasonings in some sort of non-equilibrium steady state or something like that? Or maybe it applies to also non-equilibrium statistical mechanics.
Good, very good question. Okay, so the current teaching of statistical physics requires you have a probability distribution, and the very probability distribution of some sort, or invariant measure if you want, has to take infinite long time to get. So therefore, it being told all those things you can apply is an equilibrium problem. What I showed you is, in fact, this is not true. You can definitely apply to any system with a given fixed probability. So non-equilibrium steady state is another system, at least in macroscopic world and non-quantum, you can easily show there is a probability distribution. As long as you have a probability distribution, you can use these probability theory. Therefore, the concept of equilibrium and ergodic theory are no longer relevant. The reason is the classical statistical mechanics requires mechanics as a foundation. In order to have a mechanical system having a probability distribution, you need ergodicity and you need infinite long time. So therefore, you ended with have to assume the system is an equilibrium system. In fact, the more important, they need the system to actually have a potential function to start with. Now, for a non-equilibrium steady state, you have a set of probability distribution. You can use the same thing to do a repeated measurement, and you will basically get the same formalism without this assumption. But this actually is being observed. Just nobody knows how confident we do this is. You can apply a lot of equilibrium statistical quantity mechanics with the same apparatus to study non-equilibrium system, or even time-dependent partition function. People do all this stuff without knowing why you can or maybe you cannot do it. So what I'm basically saying is this theory is much broader than all the physicists right now being told you can only apply to equilibrium system for a macroscopic system. This is not true. The probability theory can go very small system, very large fluctuation. In fact, very non-equilibrium as long as you have a probability measure.
I see. Thank you.
Yes, I have another question. So let us assume I want to derive the maximum entropy principle.
Yes.
So I'm looking at a finite sample of data generated coming from some unknown probabilities. And then I'm counting frequencies, or I'm doing empiric moment, first moment, second moment. And then I'm looking at various estimators which could recover my probabilities. So what is the advantage of the maximum entropy principle? I would never know how to answer such a question. There are many estimators. Okay. There is a huge zoo of estimators. What is the real advantage of doing maximum entropy principle for recovering unknown probabilities?
Okay, so that's our theory does not use maximum entropy principle. Any probability theory has to start with assuming you have the probability, or you assume there is one. And if you're actually measuring frequency, then you don't need to use maximum entropy principle, because the frequency in the limit is the probability. Then you know everything you know. There's no more thing to know, right? Because there's only probability, you know, everything else is derived out of probability distribution. So therefore, if you are able to actually getting a measurement on frequency, however, in the traditional statistics, until very recently, we never have enough data to construct a histogram, because the state space is always very high dimensional. you need a lot of data to actually get a reasonable construction of a frequency, also called a histogram. So therefore, in this case, a maximum entropy principle ends with try to help you to get the distribution through 1 or 2 or 3 estimator, as you said. But if you measure frequency itself, they don't really need any other. You basically just direct estimate the measure, right? So maximum entropy is only a very powerful rule when you have a huge amount of state space and you don't have a lot of data. You only have 1 or 2 estimators, but it's an infinite. It's a 50 in a 50-dimension problem. You only have 2 estimators. That is very, very low information. In this case, you can use maximum entropy to get a better distribution, but you still need a prior. Maximum entropy distribution does not let you get away with a prior. So therefore, purely based on maximum entropy principle is not a quite reasonable statement. But you could also just assume uniform. People do this. So there's 2 roads here. The one road is if you believe probability, you need to assume something. And if you assume something, if you don't know anything, you assume uniform. I guess this is the principle of indifference of Laplace. That's okay. And then maximum entropy become a meaningful thing when you only have a very low number of observable, low dimension number of observable. But when you have direct measurement on frequency, then you don't need any of these anymore. You just estimate the distribution. No.
So you say among estimators, say the maximum likelihood estimator, which is just counting the.
Oh, okay. So the maximum likelihood estimator is a completely different route. You see, I think what the statistical physics is most importantly is they are very much already fixed. What is the observable? So is the classical mechanics. They are already very fixed. What is observable? All the theory is developed based on what kind of measurement. On the other hand, in statistical community, what you observe always assume can be arbitrary. So therefore, in that case, they directly go into do estimation, but they have to assume a model. What the statistical physics basically tells us is if you only measure volume, energy, and count the number of particles, or you only measure movement and velocity, these are fundamental quantity you measure, then there's always a relationship. But the detailed relationship, you have to do engineering to get. So you need to do a lot of mechanical engineering to get a Hamiltonian, or you have to do a lot of statistical thermodynamics to get equation of state. And the general physics theory is always a meta theory, which just tells you there's such a relation called Hamiltonian relation, or there's such a relation called equation of state, and leave the more specific thing to the data to be determined. And that is very different from philosophy. Is we only measure the same thing. But in statistics, when they deal with complicated systems, people measure different things. Then the logic starts to diverge. So maximum likelihood is not based on any of these large deviations. You don't, but fundamentally they need to start with a probability space. And they don't do this kind of a posterior large deviation, maximum entropy, the thermodynamic route. So I would like to say thermodynamics is much more powerful if we all decided we only measure these quantities for similar systems. Similar means a mechanical system, thermodynamical system, whatever the system with, and we only measure the same quantity, but every system has different values. And in this case, we can build a theory. In fact, we just describe conjugate variable should have a relationship. And then the detailed data will tell you what the relationship gives you different material property, right?
Yes, thank you. And could you also explain? So you said Gibbs theorem is more fundamental than the first law. Somehow Gibbs theorem relates to symmetry breaking.
Right. So okay. So there's a one. Yes. So now we actually have a new equation which belongs to this field called nanothermodynamics, developed by Tara Hill. In this field, we have a pair. Oh, I actually didn't put that down. Let me see whether I have. So in this field, in addition, we have ds is equal 1 over t dE, and so on. You also have a new equation called dE prong equal E d1 over t plus v equal dp plus mu equal n equal d mu. We have a new equation which is completely duality symmetric with a new quantity which is sub-extensive. And this is introduced by Terra Hill. So this equation is now called Hill-Gibbs-Duhem equation, which is completely a mathematical duality relationship with this one, with a new function. But this quantity going to 0 in the macroscopic limit. Therefore, we break down, becomes Gibbs-Duhem equation. So therefore, macroscopic thermodynamics is the limit of a small system thermodynamics. In small system thermodynamics, we have this relationship, assuming we can do repeated measurement on a small system. And a repeated measure on a small system will have this quantity is not 0. So we have a nice duality symmetry. And this duality symmetry is broken in the limit of a macroscopic system because the homogeneous function of S. When S is not homogeneous, this is not 0. And so therefore, Gibbs-Duhem equation is, I don't want to use the word more fundamental. The Hill-Gibbs-Duhem equation is just as fundamental, it's equivalent to the first law. But the Gibbs-Duhem is the macroscopic limit with breaking symmetry. So we actually understand the macroscopic thermodynamics even a little deeper through the small system thermodynamics as a limit.
Okay, thank you.
So,
Are there more questions? David, you need
Just
to unmute
a
yourself.
question from other side. At the last part, you considered statistical mechanics on the basis of Markovian models. In case of Markovian model, to formulate thermodynamics, you need a concept of steady-state distribution. So it is drastically different from normal Gibson statistical mechanics in this point.
No, that's not true. Because the large deviation rate function for Markov chain is different from the Sanoff theorem. Because when you have a data which is correlated, then the large deviation actually tells the difference. So therefore, there's a new entropy function, which is under the name called the Danska-Varadon. That is no longer Sanoff. It is this function. It is this function as a pair frequency. Now, if you want project to the singleton, then you ended with having a formula here. And these are no longer looks like Gibbs theory because we are actually estimating the transition probability rate through an infinite long sequence of data. Gibbs theory really is only all those results laid out earlier. Significant part is actually assuming an IID, measurement of IID system. Or you measure something with sufficiently, the relaxation is sufficiently fast, so therefore you don't have to worry about a correlation. When you have a correlation in the data in time, the whole theory, the theory has different form. In fact, we believe what is quantum mechanical effects start to come out here. There is a correlation length in time, which lead to, this interesting result. The stationary probability now become an eigenvalue problem, with the left eigenvector, right eigenvector give you the probability.
Okay, thanks.
Yes, I remember that there were statements in literature saying that you could describe quantum mechanics as a Markov process, but then you need.
There are the issue, right? There's a coherence, there's the interference, and all these issues are what is quantum probability still considered to be very different from classical. These are all open questions. I basically feel I want to talk to many of you is honestly in US, people are much more interested in doing more practical things and don't want to ask more fundamental questions. So people are not interested in this kind of question. They want to do something more useful. But I think there's more fundamental interesting thing along this line going toward quantum physics, other kind of theoretical physics, gauge theory. You see, one thing I already alluded to several times is this theory literally put a symmetry under a Lie group, become the fundamental theory for free field. And then Hamiltonian is just a conjugate quantity to measure frequency deviate from these symmetric uniform distribution. But that is almost fundamentally the same idea as the most modern Yang-Mills theory and symmetry dictates interaction, all these language, which I don't understand anything.
Mhm.
That's why if we are able to make the statistical physics approach, maybe even possible, we can understand the high energy physics through the same logic. Because after all, two things is not known, right? Newtonian mechanics, why? Why is especially the Lagrangian Hamiltonian structure? It's just physics said it works, right? Why we doing optimization on a Lagrangian?
Now this example with John and Jesse, etc. Do you have it somewhere in published papers? I would like to study it in more detail. So
which one?
This example with coins, John, Jesse, I think.
Oh, that's one I wrote. I teach an undergraduate class last year. I decided to teach them a little bit of new things. I can send you my lecture notes. So this is basically, this is a set of lecture notes I give for my applied mathematics class.
Yeah, very good. Yeah. So you say besides Bayesian and frequentist, there is another way to think about probabilities, and this is statistical.
No, it's not. Probability has a theoretical mathematical side. Nobody argues with it. It's the what is probability, how to use it, which now has the huge amount of debate. The philosophical applied side, chromograph theory itself basically says you have to have this, right? Don't ask where this thing come from. You have to give me. And he only tells you everything after you're giving this P. But where does P come from, according to the mathematical theory of probability, is not something you should ask. You're supposed to have this. The question really is, first, where do you get this thing? Second is, how do I apply this thing? Whether is this thing an intrinsic property of a system, or it is just somehow our understanding of the system. And all these, there's too much philosophical stuff, split the whole statistical community into the Bayesian and frequency school. But as I can show you, this theorem result really tells you, you can assume anything, as long as with certain property, the uniform probably is the best. And you do the theory by actually putting more data into the theory. And now you suddenly realize physics is always doing that. Physics always have a data determinate term, starting with the mechanics called a force field. You're supposed to use data to determine that thing. Is that Newtonian mechanics doesn't tell you how to get your F. But they only tell you if you get an F, then the mathematical relation can start to compute. And the thermodynamics never tell you what is the equation of state. It's very complicated. It takes years. But nevertheless, they just tell you there is such a thing called equation of state and a bunch of relations. So it is, in some sense, much closer to observation data and parametric model than the traditional people think.
So if I may ask a question
Yeah.
regarding this subject. So If I'm understanding your interpretation of probability correctly, in some sense, you won't be able to give an expectation value for an observable before you make the measurement. Would I be correct in understanding that, or were you saying something else?
It depends on your starting point. What do you assume to have already before you do the measurement? Do you assume you already know or have a distribution? If you have a distribution, you can compute the expectation, right?
Yes. Well, yeah, let's say we don't have that.
Now, if you don't know anything, then of course you don't know anything. But according to chromograph, even you measure one, it shouldn't be the expected value, right? It could be anything. It could be the very, very unlikely, probability, very far away from the most likely value or the mean value. So the probability theory itself, when you measure one number, almost means nothing. But Bayesian wants to change that story, basically saying if you measure something, you don't know anything, this number should take very seriously. That is already starting deviate from, this is already becoming interpretation, because probability theory says there is a probability. You can see anything you want, right? A Gaussian distribution center at the 0, you can still see 3,000, right?
Mm-hmm.
Yeah.
Okay. I guess in that case, maybe I should ask it in this way. So let's say you do know the probability. It's not that you don't. If you don't know, yeah, of course, you won't be able to say anything about the expectation. But let's say you do know the probability.
Right.
In that case, so wouldn't we still need to use our interpretation of probability in some sense as an uncertainty to compute the expectation? Like, I want to say that it's still not gonna be so. I want to say that we still need to use the concept of probability in the probabilities in the usual interpretation in order to compute expectations, right? I guess I'm trying to understand how your understanding of probability will look like when we want to compute the expected values.
I thank you very much for asking that question. I actually have a little bit different view. I like to make an analogy first, and then I come back definitely about the probability. You see, probability according to chromograph is a very deep mathematical concept. We have another one, which already have almost 300 years or even longer. That is irrational number and a real line and a continuum in the space and time, these concepts. These are mathematical concepts. I think you cannot understand these concepts through our daily experience, period. What you understand is practically just learn the mathematics, learn the way of thinking. You allow me to use a more exaggerated word. You're being brainwashed, just think these are okay. Then we don't question these things and we use this powerful idea and tool to understand something else, more real. Probability is exactly one of such things. We should learn the mathematics, being brainwashed before we use it. Unfortunately, the education on probability comes way too late. So therefore, the worst is to physicists, they already learned so much other things. They can never no longer being brainwashed about probability. So then they encounter all the more real problems. And you're trying to understand something so refined through much more crude daily experience, right? So therefore, I suggest we should try to take and accept some very fundamental mathematical concepts like a continuum, irrational number, probability, including the expected value as a concept, and then trying to use them to understand the real world. In this case, the relation is not trying to understand this concept through example. It's trying to use these concepts to explain the real world. And this relation, in most cases, doesn't matter. You can understand back and forth, but when you have encountered two fundamental concepts, people still argue irrational number, what is it, right? You can still argue today irrational number, but people stop arguing because somehow we already feel like there's no longer need to be argued. Imaginary number. There's such a thing, but the probability comes way too late in the education. That's the problem. You see, this simple example really is very important. Chromograph says, anytime you do one measurement, you're supposed to fix one of the elements in this thing. There's no such thing as a partial information from Kolmogor's point of view. Kolmogor's point of view only conditioned this way, but then you realize that Kolmogor's original assumption is no longer even relevant. This little subtlety, I really believe, should be talked about by any, maybe fifth grade. You see, intrinsic property, a coin is gone. You assume the P and 1 minus P, but up to here, it's no longer there. It's there 10 coin, 1 up, 9 down. Where is this P?
If I may interject, wouldn't you say that the P is in the large end limit? So in some sense, you can recover the P. In
large
limit, right?
end, yes, this is the frequency school. Yes, if you believe frequency school, yeah.
Okay, so you're saying, but in the let's say finite end limit, that's not at all clear. Is what you're saying? Right?
Yeah, but
so we need a different term.
But there's no such thing as in the limit. In the limit is a mathematical construct. So therefore, we just logically run the whole round. In fact, large deviation is strange. Large deviation is when n already go to infinity, I still don't observe P, right? So therefore, this is exactly the kind of discussion we need to understand the probability better.
I see. Okay, thank you for that. Yeah, thank you for clarifying. Yeah.
Sure.
I had a question which I didn't finish. So I remember that there were people in literature trying to derive quantum mechanics from Markov processes, and they would always stress that in addition to Markov processes, in addition to the statistical regularities you mentioned, you need also negative probabilities. Now, do you by any means have an idea what negative probability means?
No, I don't. There's quite a few quantum mechanics inspired modern mathematical theory, free probability, all this. I don't know anything about it.
So do we have more questions?
So I have a vague question about the entropy.
Go ahead.
I'm not sure how to ask it very precisely, but I mean, in a way, in this theory, entropy appears as somehow is derived from this rate function, right? In this large deviation law, right? And have you checked whether this notion of entropy satisfies the Lieb-Ingvason axiomatics? I don't know if you know it. Somehow Lieb and Ingvason, they sort of developed an axiomatic theory for determining entropy in thermodynamical settings, and somehow it combines, like, it, you know, it's a theory where you sort of introduce an ordering between states of the system.
No, right. I think I know a little bit about those theory. You see, I like to do one project, which clearly, if anyone interested, I like to not work on the entropy of Shannon or relative entropy, which is all the literature now. I like to work on this entropy, see whether the axiomatic relation still is true or not. This Danske-Varon entropy, because clearly, according to my theory, there's many different entropies. This is the next one, which is a much more general. And this entropy no longer have the simple additivity. So therefore, there are certain things, but you could say this exactly maybe the more interesting thing is, clearly there's more entropy than Shannon or Sanoff or relative entropy. This is my point. So any axiomatic theory built on that way, we like to apply the same mathematics to this new entropy, whether we can still get the axiomatic result or we can modify it, it will be very interesting and important. So there's a lot of
Thank you very much.
open new questions to do.
Right, right. Thanks.
Okay, so I have one vague question also myself. Once you are teaching a lot, apparently more than we do.
Excuse me?
Once you are teaching a lot,
What am I teaching them?
could you explain why both probability theory and thermodynamics are normally very difficult to understand and very, very unattractive for students? Why students are normally afraid of both thermodynamics and probability?
Okay. So I'm in some sense, I'm in a wrong department. I don't teach any physics. My students, nobody knows of my students. Even majority of my graduate students don't know thermodynamics. I'm in the department of applied mathematics. My students know a little bit of biology, know a little bit of probability theory, know a lot of differential equation. We do mathematical biology. My own research is different from my teaching significantly.
Oh.
So therefore, I don't teach thermodynamics. I do teach a probability theory, a more applied probability theory.
Mm-hmm.
So I don't teach them more. So this is just combining my past interest with my current teaching a little bit, but I don't teach thermodynamics. In fact, you notice this slide has no thermodynamics here. This slide is just purely simple probability, this thing.
Mm-hmm. Yeah, I see. Okay, so do we have more questions, comments, or ideas?
Thank you very much.
Yes, thank you very much, Professor Qian.
Thank you for inviting me.
Please don't forget to send us your teaching notes on.
I will. Thank you very much.
Could you please also share the slides?
Yeah, I will.
Thank you.
Okay, bye-bye.
Thank you very much for your time. Goodbye.